glad that I got mine out of the way. I could not imagine.
Oh, I bet you are. Yeah. That's nice.
Oh.
Wow, you must hate your life.
Okay, let's get started today.
Let's do it.
We got one last lecture today on rubber elasticity. Then this Thursday, we're going to go through the whole courses. And we will have a short quiz, very short, 10-15 minutes. And that's going to be only quiz for this class. Then after the quiz, we're going to go through the review of this class. I always like to do a review. I feel in the end, I hope we can condense the whole lecture down into 1 or 2 sheet of paper that you can remember 1 year from now, hopefully. You know, after a couple of years, I don't even remember what I was taught in my graduate school. So it's good you have a cheat sheet in future. You want to go back and take a look if you're missing some point. Then next, the week of December, it's going to be the final week. And our class is scheduled on, I believe, somewhere between around 10:15 a.m. on the Thursday of next week. I'll send an email to everybody so everyone can be on the same page for the final test. The test is going to be about 1.5 hours long, and it will cover 3 chapters. Okay? And we will, as I said, the next class Thursday, you don't want to miss this class. This is the most important class ever for this lecture. We will cover the key point for the lecture. We will have a quiz, and I'll carve some time for help session as well on this Thursday. Okay? All right, so how about today? The chapter 10. We have a little bit left on rubber elasticity, and let's finish this chapter up. It will probably won't take even, will not take 1.5 hour long, probably 15 minutes. We will cover the rest of the rubber elasticity. So what we're going to do today, we're going to first review what we talked about. So hopefully everybody remembers after a couple of turkeys and drinks in the Thanksgiving break, where we were last time. Totally don't remember, right? That's the magic of holiday break. So we talked about rubber elasticity. Why the rubber string is behave like elastic material. So let me recap what we talked about. We discussed rubber elasticity. So what we talked about is where the elasticity comes from. Where it comes, we covered that elasticity is come from changes delta S upon stretch. So we discussed when you have a rubber string, you have a network. Before you stretch it, you have a certain entropy into the system. And while you stretch it, your chain is elongated. So this is original state. Once you deform it, you basically lose entropy upon stretching. And that entropy contributes to the elasticity, right? So as we know, we won't go into too much detail, but we know there's such a relationship in how many configurations you could have in the system and how does it depend on the K. So this is a reason why there's rubber elasticity. Okay? We talked about this, the origin of that. We talked about what the changes in the delta S before and after. And we basically come into the conclusion that the delta S is very much related to the draw ratio, or how far you pull it. You pull the system of the chain. So if you recall, we would have this that's a deformation in 3 directions of the chain. So while you deform the strain in 3-dimensionally, lambda is the draw ratio in x, y, z direction, and how it influences your delta S. Okay? That's a very generic equation showing how would the delta S changes, or how you would lose entropy upon poling it. And in a special case, in a very much later part of lecture, we talked about in the case of tensor draw or tensor pull, where we basically pull unidirectionally in a draw ratio of lambda. So if we have an original of our cube, we draw it to be longer than what in one direction. What the entropy loss would be, right? In this case, you got, let's assume this is x direction, this is y and z. We know the new Lx, it's called x, y, this would be Ly, and this will be Lz. While you're pulling in one direction, you only deform in x direction as a draw ratio of lambda. And lambda basically means the final L x will be divided by Lx0 would be lambda. That's the definition of what the draw ratio, right? And I hope Professor Gilbin has covered it very well in this one direction pull. And if the material is ideal elastomer, we know according to the Poisson ratio, the other direction gonna shrink, and gonna shrink at the ratio of delta lambda. So Ly divided by Ly0 gonna be 1 over root lambda. Because while you pull it one way, the other two directions going to get smaller. Okay? And same for the last direction of Lz divided by Lz0, going to be the same. So we talked about this special occasion, how your delta S would be changed. In this very special unidirectional polling methodology, your lambda x, lambda y, lambda c can be written as much more simpler form, where you get divide by 2. Now lambda x square going to be lambda square. Lambda y square going to be 1 divided by lambda. And you're going to plus lambda z square, it's again 1 divided by lambda and minus 3. So this would be a case where you have a film and you just draw it unidirectionally. That's the entropy you would lose in x, y, z direction. Right? Lambda y, lambda c, where lambda x is basically equals to lambda. Lambda y is equals to, this would be the lambda y, right? So this is lambda x will be equals to 1 divided by root lambda. And lambda z direction will be the same. So that's how much entropy you lost. In the special case where you just pull the film one directional but not two directionally. Okay, everybody following this part? So that in the last 10 minutes of lecture, where everybody almost fell asleep, where we talked about through the first principle of thermodynamics, we can have a relationship between the force and delta S and draw direction L. Okay? Instantly, yeah?
The delta S equations, when we finished up in class last time,
Yeah.
we canceled the n.
We canceled the n.
Yeah, the nb squared canceled with the other nb squareds.
Yeah, so that is different n. So this n
So this
is
n should be
number,
here.
yeah. So this n is number of crosslink point in a unit volume, okay? And the other nb squared is number of bonds inside the one chain.
So number of cross-linked.
Point. So if you have, let's say, if you have a rubber band, anything in the, for example, assuming this, if you cut the uniformly volume, how much number of crosslink point? That's the definition of this n here. And the n you talk about, last time we talked about, that's number of the bond along the backbone, right? MB squared is that.
But you did give us an equation that is identical to that without the n on it?
Yeah.
So not this big n, but your...
Right, so that's for individual chain. So this is for as the system. So unit volume, per unit volume. So that's where the number n is coming into play.
Okay, so wait, so this one's per unit volume.
Now the one without n is per single chain. Well, you just pull one chain. There's no other chains.
Okay.
But now we are talking about collectively. For example, this class, we got 13 of you guys. So we're talking about 13 total number here. Okay? Okay. And you will later see why this come into play, because while you have a real material, you need to consider the cross-link density. And that's related to this number n. The higher the cross-link density, this n will be higher. Okay? So where we almost ended up here in the last class, but we had a little bit more time while we did a partial derivative of this equation, where L is basically related to the lambda. And we know what the delta is. I wouldn't go into too much detail, but what we would get is we can first convert this to partial derivative of lambda instead of L, because we don't have anything in the equation. The relationship between lambda is L divided by L0. That's the draw ratio, that's your final length, that's your original length. And if you take a derivative of lambda, you can convert it this way.
What is F a measure of again?
F is the force upon pulling the film. Okay, that's a measurable force. It could be Newton or, millinewton, or just a force exerted on the rubber band. So if I have a rubber band in my hand, maybe we can use this one as an example. So imagine this elastomer piece. Oh, that's great. You're such a good helper. Good. So we now have a real rubber band. It has a certain volume, right? Imagine this is a cross-section of maybe 3 millimeter diameter, and there's two of them. Well, you start to pulling it, you start to feel forces being exerted on it. That's a force F. So we are calculating how much this force is. Force is expressed as a Newton or millinewton or nanonewton, this type of unit. But it's basically, this equation tells you how does the force relate to the entropy loss. That's the uniqueness of the rubber band, okay? Because while you pull it, as I mentioned, before I pull it, if I zoom this thing 1 billion times bigger, if I have the superpower to look at individual chains, that's what happens here. Okay, so before I pull it, it's like a coiled one. It's very much coiled up. Well, I start to pull it. If I pull it twice long, this bond, this end-to-end distance will increase twice, right? And that's resulting in a reduction of entropy. And because of reduction of entropy, we will have a force, can be calculated how much result of that. And entropy partial derivative of the draw direction, that directly is force. If we do the math here, we will get what the force will be after I pull in the rubber band. And there is one question. We mentioned that in this case, we are talking about one chain. But in the rubber band, if I zoom this thing at 100 times bigger, there will be a cross-link point, and there will be another chain. Right? You have multiple cross-link points randomly distributed around the different point of polymer bonds. And this particular n here is talk about if I count how many number of these individual chain or cross-link point, that's what this n is. So you can have cross density of 10,000 cross-link point per centimeter square or millimeter square, or 100,000 times cross-link point. The higher these cross-link point, your network is more dense, right? You could also have loosely cross-linked point.
So that prevent you from losing entropy.
We will see. Yeah, we will see how does cross-link point affect our network. Okay, just in a moment. Let me recap what we did last time. If we take a partial derivative of this, we can basically reach how much force we would get. So it will be, again, minus t divided by L0. We can take a partial derivative of that. This will be minus nkt divided by 2, multiplied by 2 lambda, minus. Okay, so if we simplify this even a little bit more, what you will reach a conclusion is you will get nkt divided by L0 lambda minus lambda square over 1. So that's how much force is happening at this rubber band. Okay, you can derive, you can plot this thing out. And this is measurable. That's how much deformed it is, right? Lambda is 2, it means you're twice longer. F is force. You can measure it as well. If you have Ingstrom, you can just probe, how much force I actually sense in the rubber band. It's actually something look like this way. If you could plot out this equation, lambda minus 1 over lambda square. At high draw ratio, lambda square will becoming negligible. Think about this would be draw ratio of 10. 10 square, 1 divided by 10 is very small. So at high lambda, this will become a linear. But at low lambda, it's not a linear one. If it's a linear, that's like hook spring, right? So that's what. How does the force depend on draw ratio? What we got. So that's where we stopped in the last class. We finally get to a point where we can use the theory to predict. Using a very ideal model, we use the Gaussian chain to understand if you pull a rubber band, how much force you would have depending on how much you would pull it. And this would be, vertical axis would be the force, okay? Force versus lambda. And it's basically, this is the force equals to this equation. There's other parameters actually people want to know. One of the commonly one is what's the stress-strain behavior, right? So for the first part of the class, we're going to talk a little bit about what the stress-strain behavior. So how does stress is being expressed?
Force over area.
Force over area, and you guys probably know the difference between engineering stress versus the true stress, right? No?
Yeah.
Some of you guys? So, okay, let's explain.
I said let's assume we don't don't.
Okay, good. So let's talk about this concept first. So I want to go back to this example where we talked about here. So what is engineering? Engineering stress. Engineering stress is defined by how much force you divide by A0 or initial. This is initial cross section. Okay? What does this mean is look at this diagram where you have 3 directions, right? X, Y, Z. So the force is applied to this side of the cube, where initially how much the area this side is. It's going to be this dimension, Ly0, right? Initial length in the y direction, and initial height in the z direction. So that would be the answer. And the engineering stress doesn't consider the change of area, because if you look at this case while you draw it, I like this rubber band at one time. So in the initial cross section is about 2 millimeters in diameter, but while you pull it, it's getting narrower and narrower. So engineering stress doesn't consider a change of area. It just plot out as how much force you measure divided by initial area of 2 millimeters square. True stress, which is, as the name indicates, it's measuring what is really the stress in this rubber band. So it defined as A divided by AX, or in the deformed state, how much area is. This area will not be the same as where it's starting from. So true stress measures at any given moment what the cross-section area is.
So it's the instantaneous stress.
Yeah, I mean, you cannot measure stress in a test. What you always measure is just force, how much Newton you sensed. And stress is calculated by force divided by area. So that's why there's 2 explanations, right? Divide by original area, you assume there's no change, or divide by the real-time area, wherever the state is. And they has a very simple relationship. As you saw, there is a connection between lambda z and in the draw direction. So turns out to be these. It just matters about 1 draw ratio. So
is engineering modulus more accurate for brittle, more amorphous materials? Given that they tend to break without much change in there.
I mean, true would still
Area.
True would be the same. I mean, if it doesn't change in the cross section area at all, it would be the same as engineering. So engineering is never more accurate. It's just easier.
Yeah.
To measure.
Easier to do, because while Chris mentioned, you don't have always a good way to measure how much cross-section area for a sample while it's being stretched. So, however, you can measure this length. If you assume it's elastic, incompressible material, you draw in one direction, it's getting bigger. The other 2 directions are going to be shrink at the same volume, right?
Right.
You got this?
Yeah.
So that's why this would be always a factor of lambda. So in other words, the true stress is always F times, or lambda times engineering. Okay? If you draw it 2 times the length, your true stress happening in the film is twice of what you measure by engineering. Okay, some of the background knowledge for these 2. So let's take a look at the true stress first. We know what the F is. We know what is cross-section area is, right? Cross-section is Ly, Lz. So F divided by Ly, Lz would be the answer. And if we kind of put this equation into it, we will get nkt divided by L. So because this is L0, or basically Lx0, because this is a draw in the x direction, multiply by Ly, Lz. And you have the second part. And if we want to convert this to be the volume, because you multiply x, y, z direction, and it can be converted into volume, you can get what is, what would be the true stress depending on the volume, right? So how does this work out? So let's first know what is volume is. The volume, where our film starts from, will be Lx0, Ly0, and Lz0. So multiplied by 3 x's would be your volume. And there's a tiny little bit difference between these two equations. That's where Ly and Lz versus Ly0 and Lz0. And we know there's a connection there. How does these depends is basically another lambda. So this can be converted to volume. And you multiply by lambda. And this lambda comes from Ly and Lz relationship with Ly0 and L0 relationship. So it's basically here. Okay? Okay. And there's one piece we need to put in. So your true stress for the system would be nkt divided by V would be equals to lambda square minus that's your stress in the system. And we're going to go one step further, because if you know the stress in the system, we can calculate a universal parameter for the material. That is the modulus. The modulus is some of the most important parameter for the elastomer. You know, elastomer is much softer than glassy plastics. Elastomers are typical on the order of megapascal level, while the glassy polymer or material or structured material is on the gigapascal or tens of gigapascal. And you can have carbon fibers, you know, hundreds of gigapascal, which make them really rigid. So someone help me, what would be the elastic modulus defined as? Stress over strain, and it has to be in the elastic region, right? So typically people think it's first 1% of deformation or 2% relatively. So you can have, let's say, let's use this. We are taking a limitation at lambda close to 1. Then we take a partial derivative of true stress. Divide by lambda. and we have a relationship right here. If you take partial derivative to the lambda, this will become 1. 1 minus 2 lambda will become, let me do it here. So we will have nkt divided by v so this will become 2 lambda. This will become minus or plus 1 plus lambda squared, right? If you take partial derivative. And when lambda approaches 1, this will be 1. 2 multiplied 1 will be 2. So this would, you come into the conclusion that your elastic modulus of your rubber band or rubber string is equal to number 3. It's a constant. It doesn't depend on anything else. What is n? Number of cross-linked points per, number of cross-linked points. V, we just talked about. It's a volume. K is constant. T depends on temperature. So we come into several interesting conclusions. As you see, we know E, or elastic modulus of a rubber band, is linearly dependent on the T. Is this what we talked about at the beginning of the class? Well, if the temperature goes up, if you hang something below the rubber band, it's going to shrink instead of relax. That basically explains what happens in that case. Your elastic modulus goes up versus temperature, so it will getting more and more stiff for the rubber material compared to the metal material where it's entropy driven, so you would have relax of the metal spring getting longer, okay? So that explains what this T is. K is constant, so there's nothing to depend on that. The other parameter that is interesting is n divided by v. The n is number of cross-link points in the system. So n divided by v is tell you how heavily you cross-link the material.
So like cross-linking density?
Yes. So the higher the cross-link density, according to this theory, you would have a higher the modulus. So we can actually do some other ways to express this. The other way would be, we know the density of the material, we know the volume of the material. We can also convert this to be another parameter is the molecular weight between two cross-link points of the material. Because if you write this in this way as E, it gives you another perspective. How does this work out? So there's missing a 3. So 3 rho is the density of your material. R is another constant, and R and K has an number, Avogadro number difference. T is the same, and Nx is the cross-link, the molecular weight between the cross-link points. So these are inverse proportional. So N versus N 1 divided by Mx, okay? But they're talking about the same thing. How does we rationalize density multiplied by volume would be how much material you have. If you use this top, N multiplied by molecular number of the molecular weight between the point, that's also the total number of your material. So you can use this relationship to understand your system. In other words, if you know you have your how big your material, you know the cross-link density per volume, you can calculate how much crosslink points you have, and you can have the molecular weight between the crosslink points.
Wait, can you repeat that? You said what? Can you repeat that?
Yes. So you can get the crosslink density, n divided by b is how heavily you crosslink it, right? That's one way you can view the system. There's a second way you can view it physically is what's the molecular weight of your segment between each crosslink point. They're talking about the same thing. If you crosslink the polymer 10 times more dense, the distance between two crosslink points will reduce by 10 times. It's reflected by the molecular weight, or mx here, okay? Let me write this down. So mx is molecular weight of the chain between two crosslink point. The higher the crosslink density, the lower the mx will be. There's another parameter is shear modulus. And how does the shear modulus depend on the tensor modulus? Chris, I know you know it.
It's like 1 over 2. It's 1 over something with Poisson's ratio, and the number 2 in there as well. But
Negative Poisson over E, and some other variables splashed in there somewhere.
So G,
shear is 1/3 of E. Yeah, that looks a lot better.
2%, no, I think.
E over 2 was.
Okay, so or basically it's just about 3 times smaller, because for incompressible material, this Poisson ratio V is equal to 0.5. So you can get, basically you can also know the shear modulus is going to be exactly 1/3 of the value here.
You said Poisson's ratio is 0.5 for what type of materials?
For incompressible material or rubber material, where you pull it in one direction, in the perpendicular direction, your your deformation is half of your tensor direction. Okay, so it was quite a success for the community to see this type of understanding in the rubber material. It explains why Rubberband would contract. Explains why rubbers would be. How does the rubber material depend on how you crosslink it? And so the community was very happy to see this, right? Because if you know a certain modulus you want to get, you can roughly know how much you need to crosslink to. Because elastic modulus have directive proportional to crosslink density. And there's another thing you can see in this equation. There's no dependence of what a chemical bond you cross-linked. So in this physical model, it doesn't care if it's what type of chemical bond you have to form this link. It only matters what's the length between between two cross-link points, how long that is. Yeah. So that's related to this mx, and you can use this to estimate what a typical rubbery material is. Let me do it here. So if you know, for example, a typical rubber band has a density about 1 grams per centimeter square. That's about right for most of polymeric material, right? So let's copy the elastic modulus, for example. 3 times rho RT divided by nx. So let's say you make a rubbery material. You know the density would be about 1 grams per centimeter square. That's a typical density for a plastic material, right? And you know what I is, you know what temperature is, and actually you can just say a typical rubbery material has probably this much molecular weight between the cross-link point. And you can see this is about 10 K, so relatively high. So these rubbery material usually have a pretty good molecular weight, okay? So mx means, now I'm going to draw a simplified model. So that is the mx, the molecular weight between two cross-link points for this material, okay? And you can calculate E would be equals to this equation, right? So if you do the math correctly, this you can get, it's about 0.25 megapascal. That's pretty good in terms of theoretical descriptions for the rubber material. It's on the same of order of magnitude for the rubbery material, okay? And if you do, and if you have mx in case of 10 times smaller, and you know elastic modulus is about 2.5 megapascal. So this is also can be measured for rubber band material. Okay, we can take a short break, then we can come back to discuss some of the limitations about this theory. We talked about many good parts about this theory, how you can understand, use this to predict the mechanical property of rubber band. And we're going to spend another 15 minutes to talk about limitation after 5 minutes break, okay?
So for this problem, we're given the stress, and we have the density, and we're solving for mx.
Mm-hmm.
The only way we've related E with sigma true is through the partial derivatives. Is there another way to relate it?
E and the
Sigma, wouldn't this be the true stress?
true stress and engineering stress is just a factor of lambda difference. So if you check this equation, where this would be your true stress, right?
Mm-hmm.
And this would be your engineering stress. Will be lambda kt v and lambda minus lambda squared over 1.
Mm-hmm.
So it's just a factor of lambda difference. Is that what you're looking for?
No, so I was just looking at this. We've got the density, we've got the molecular weight of the polymer before cross-linking.
Yeah.
So I'm assuming we have to use this equation because density, and we're solving
Let
for
me read
mx.
this.
Okay.
Yeah, that's exactly. So if you move this on the other side, you can get what would be the mx would be equal to.
This is this sigma, or is this?
No, this is sigma.
This is sigma. Okay.
Yeah.
So how does sigma relate to E?
So this need to be divided by the strain.
Okay. And that'll relate it to. Okay, right, because this is. Okay, but I don't have the strain.
So it's 100% elongation. So
That's
strain would be 1.
1. Okay.
Or
So-
draw lambda would be 2 in this case.
Draw lambda would be. Why would it be 2?
Because
Because you
lambda is equal to the final. So
Yeah.
lambda is equal to strain plus 1. This is
Okay.
called draw ratio. So if your film is originally 1 centimeter, you pull it to be 2 centimeter. That means 100% strain, or 200% draw ratio, or twice of the draw ratio.
Okay.
Yeah.
All right. So that's what I don't even need this equation. All right,
Yeah.
that makes sense.
Okay.
All right, thank you.
Yeah, you're welcome.
This is 1, and then this is 4. Because it has part of the stem growth article. So it has this little backbone right here, because that counts as 4. And so there's a lot of them that have weird count. Yeah. But this fucks up your stem. So like, that's why it's like 3 over here, 4 there. This is Josh Tropp's final that I did. And then there's in 2. It's like the same deal because it was very similar problems.
Mm.
So are the limitations we're going to be talking about, do they apply to the
Mhm.
change in entropy stuff as well?
Yeah, we will briefly cover
Okay.
what's the limitation. Does everybody have the homework? Except to Rebecca?
So when is it due?
It's due this Thursday, no. I thought I have 13 copies. It looks like,
I thought there was 2 next to the computer.
yeah. So the math doesn't seem right. You will have 13 people in the class?
Is one Nathaniel's?
Yeah.
Oh, yes.
Yeah.
Did Dana get one?
Yeah.
Okay. Huh. Yeah. Okay. As long as everybody got one copy, that's good.
What's the quiz on Thursday?
I cannot tell. Otherwise, it's not called quiz.
Tell me.
No. You need to guess it.
Should we study for it?
You can go back a little bit in your notes, but I wouldn't expect you study it.
So generally, understanding is a good
Mhm.
strategy here.
Mm-hmm. Yeah. And it will take probably 15 minutes for the class to go through the quiz.
It's a long time for a quiz.
Is it a long time? I think it's... no, if you can finish it in 5 minutes, you can finish it in 5 minutes. Okay?
Is it multiple choice?
No. So let's talk about the last part about the limitation. I'm trying to reproduce this curve where we have a deformation of the chain. Okay? So this would be a magnify of these cross-link points. So what would be the limitation for this theory? I mean, it sounds very promising for many aspects of it. We know.
Doesn't take structure into account.
Yeah. Yeah. Huh?
Doesn't take structure into account.
Yeah. It does not take many things into account. You know, we made several approximations. So number one thing is we did not consider changes in entropy. I mean, it's small, but it's still part of it. And interestingly, while you have a rubber band, if you pull it, there's some temperature difference. And interesting enough, there was a very, very funny video on the YouTube, or a concept, where have you guys played with a rubber band? If you pull it fast enough, it's actually going to get cold.
Cold? What is it?
It's going to get cold.
Wait, doesn't it get warmer?
No.
If you pull it really fast enough.
Yeah.
Pull fast bonds, so there'd be bonds breaking.
No, not relate to the bond breaking, but relate to the
The
intermolecular.
surface area so fast. It's like
But yeah, but get a raw rubber band without any wrapping to it. If you pull it, you stick to your nose or your skin. You can sense it's actually get a little bit cooler. All right, that's because in this case we actually didn't consider there's any difference in temperature. But in real case, when you pull it, it will get cooler, a few degrees, actually quite significant. If your room temperature is 20 degrees, that's about like maybe 10, 15 degrees cooler.
Is that by convection?
No, it's just by intermolecular forces difference while you pull them. While you let it go, it will heat up and getting warm, higher than room temperature. It's an interesting concept, like more like a AC conditioner. While you need to generate a cycle of heat and cool, right? So someone, I think he is very crazy. He made hundreds of rubber band, and he tried to make an air conditioner out of it. It's a hand cranked. So the concept is, it's a wheel of the rubber band. So on one side, it's keep pulling it, and on the other side, well, it's always relaxed on the other side. So he's hoping you can generate enough cooling force for that. You can actually probably watch it on YouTube somewhere. People do that. But it's just not enough efficient to do that. It's much slower. But I encourage you guys while you go back, and if you have a rubber band, just without any like a close wrapping to it, you can actually certainly sense that. So that's one limitation for the entropy. And second is, we didn't consider change of volume. So while you pull it, it's not a perfect, a Poisson ratio of 0.5 or perfect. Especially while you pull it at very long, it's more substantial in this case. There's two minor things. Is while in this case, we assume every point in this will follow a Gaussian deformation. And that's a bigger problem for the theory, is it at low draw ratio, this is okay for Gaussian chain assumption. At high draw ratio, your case is no longer valid. And this is the biggest problem. Well, at low draw ratio, you can assume the cross-link point between these two are more or less a Gaussian point. But while you pull it much further, it's almost linearly extended. So your MB square or free joint chain doesn't apply to that kind of model. Okay, so there's one more, and I think it's minor, is where I kind of assume the cross point is affinity to the cross-link point is affinity to macroscopic deformation. What does this mean? It means, like I draw the rubber band, if I pull it twice the length at macro scale, it will deform twice the length. But that may not be always true. Well, especially in the networks where you do not have evenly distributed cross point. If somewhere, while you pull it macroscopically, deforms more than the other, then you need to adjust for the theory. But still, even with these three, let's take a look at an example where people actually measured versus prediction. How do they compare? So, if you have plot a stress strain, again, from our theory, I draw you once, it will be something look like this. You can plot stress versus strain curve for ideal case. But in the real case, let's give it some number. Draw ratio of 5, 7, 3, 1. This should be here. 1, 3, 5, 7. So these are just tell you how long you pull the rubber band, okay? And in the real case, at the lowest number, you can actually measure them experimentally. They're relatively going well, okay? Matches pretty well. If you go to textbook, they have more precise version of this. Then after, in this case, at a draw ratio of 5, you start to deviate a lot versus theoretical prediction. And this difference is coming from mostly this part, okay? This would be the biggest challenge for the field to solve. And there are several theories we're not going to talk about in more detail, but you can modify the system to look into that. And there's a small chapter in chapter 10, you can look into that to get more detail. But for our class, our understanding needs to be how you interpret the modulus depending on cross-link density, and how you interpret the stress strain curve depending on the draw ratio, okay? And last thing I want to mention is this is not a linear in stress strain curve. And that's also being captured by the theory that your stress strain curve is not a linear relationship, okay? There is a dependence of minus lambda square coming to this. That's also being captured. So kind of a pretty good theory so far, okay? So we finished this chapter as well for rubber elasticity. Any question for this chapter so far? And there's one minor point that I will address to you guys is there's one more thing is an interesting phenomenon we will cover as the last chatting point of this chapter is we talk about the rubbery material. There's another important class of the polymeric material is gel. Okay? I actually deal with it every day. While you think about, there are several examples in our daily life is related to gel. Jello is one, or super absorbent material is one case, where baby diaper is an example where it can be expanded 100 times. So in the next lecture, we will just talk about how do we explain a gel, a cross-linked network, how far it will be absorbing material and expand. It's an interesting question because it's combined the question we talk about in the chapter 2, or chapter 7, where we talked about Flory-Hagen theory and material. And we also talk about in this chapter about rubber elasticity. When you think about swelling a gel is you deform the network to be a gel, to be much bigger the network. So there's two competing forces there. One want the gel to swell, that's osmotic pressure. They want more of the solvent going into the system to reach your equilibrium. But your material is also cross-linked. So they can only swell to a certain extent, and we will talk a bit more in the next class. And then we'll wrap up the whole chapter, okay? All right, that's it. Yeah?
For the final, would you consider letting us bring in a one-page handwritten note sheet rather than the equation sheet you give us?
No, but I have better news for you. I will do that for you. I will provide one cheat sheet for all the equations at the end of the test. So you don't need to memorize most of it.
Equations in polymer physics, not all the equations we need.
I'll do my
Is there a
best.
way you can have that available to us before the exam so we can have like at least an idea of the layout so that when we're on the exam we're not trying to figure it out there too?
Yeah, I can do that. I have no problem for that. Okay?